Okay, my name is Ruth Aloni Lavi, and I'm coming from Gong Company, and I will speak today about context-aware classes in speech recognition. The agenda for today, I will start with Gong, with describing my company a bit, then... לא שומעים אותי? Okay. I will start with Gong, describing my company, then I'll give a short introduction to ASR. I'll then continue with explaining the motivation for the work that we did, and then I'll describe the class-based model, I'll present the result we received, and I'll end with a short summary. So, Gong. Oops, sorry. Gong Company actually helps salespeople to perform their sales conversations better. We record and analyze each coming call, emails, and any other data, and extract analysis out of it, and thus can help the salespeople and the managers to understand the conversation flow better and also understand how to improve it. Oops, sorry. The company was founded 4 years ago. We have more than 260 employees. We have raised more than $160 million up to date. And the company also serves many known brands such as LinkedIn, NASDAQ, General Electric, etc. It is also a very cool company for data scientists since we have a huge amount of data. Okay, so when before Gong was in the sales domain, salespeople received such a long line with their recorded conversation. So they had a 50 minutes conversation, and what they could do, they could just listen to it. Which was non-realistic to listen to all their calls, of course not to their managers. Nowadays, what they have is lots of information. They know who spoke when, they can understand the call structure, the topics of the calls, what was shown, and what was said. And I will going to concentrate today on the speech-to-text, the content of the conversation. So not many years ago, the situation of speech recognition, automatic speech recognition system was not that good. I mean, there were dogs that were saying woof, and the system was recognizing it as meow. And people like SpongeBob had to repeat their phrases many times until the system understood what they've said. But today things have improved thanks to DNNs and thanks to many other things. And speech recognition systems are working almost like humans today. So what is an automatic speech recognition system? We have the input signal to the left, which is an energy signal that you have many points each second, something like 8,000 measures of the energy of the signal. And the output of this system is the text that was uttered in this audio segment. What is going on between? On the first stage, the energy audio is transformed into a signal representation, or what we're calling in machine learning, it is the stage of the feature extraction. And this is done in many different ways, but once it is done, we have per small frames of speech a vector representation of the speech signal. And this is entered into the recognition system, which is composed of three main structures: the acoustic model, the language model, and the lexicon. The three of them combined together are performing their recognition stage, and then the sequence of word is being extracted. I'll elaborate a little bit about each of the three parts. Let's start with the lexicon. What is the lexicon? The lexicon is the list of words that we plan to recognize. In a spontaneous conversation, it can hold hundreds of thousands of words, when each word has its pronunciation, its phonetic transcription. And if this word has more than one pronunciation, then we'll have two phoneme representation for this word. Now, suppose in the real world, we are going to work with a new customer of Gong, which is a small new company with a very new name that was invented 2 weeks ago. And no one has seen it before, so of course it is not one of the words that exist in our lexicons. So what do we do in such case? Well, we can hire a human phonetician that will sit and transcribe each new word, but this is not realistic if you are having hundreds of customers. So what we're doing is that we're applying a G2P statistical algorithm, a grapheme to phoneme. And this algorithm translates the sequence of letters or grapheme into a sequence of phonemes, of the phonetic representation. These algorithms are trained on a huge list of transcribed words and learn the statistics of the transformation between the sequence of letters and the sequence of phonemes. So now we have the lexicon, and we know how to add new words. And now we're going into the acoustic model. The acoustic model receives the acoustic features and extract the phoneme probability. And it is usually based on a complicated DNN, and it is trained on a very large amount of audio conversation, of transcribed audio conversation. Okay, so now we have the lexicon and the acoustic model, so actually we can do the recognition. But why do we need an extra unit? Well, look at this manager. He says, we need a better speech recognition software. I told my employees to celebrate their diversity, and the computer thought I said perversity. So this is an uncomfortable situation. And why does this error happen? It happened because the sounds of those two words is similar. But of course, they appear in a different context. So in order to get the context information, we need the language model. There are different language models. In Gong, we use the n-gram-based model, which is the statistics of n words. For n equal 1, it is the probability for each single word to appear. For n equals 3, it's the probability of 3 words to appear. And how do we learn this model? Again, we get a huge corpus. This time it is only text of spoken conversation. And from it, we just count the number of appearances of each single word, the number of appearances of pairs, of 3 words, etc. And then we use different statistical model to get a good estimation of each word depending on its previous recognized words. Training this ASR system, as I've said before, require a huge amount of databases. For the acoustic model, we need voice and text. For the language model, we need text. For the G2P, we need the lexicon. We use both supervised and unsupervised data and external and internal resources. Okay, so now we have the whole parts of the system, and we want to do the recognition. Now we want to do the recognition in an efficient way, near real time, or at least near real time, and not to use too many computers resources, so it will still be valuable to Gong and to its customer to use this ASR system. So what we do, and what is generally being done today, is that the speech recognition is done on top of WFST structure, which is weighted finite state transducer. These are automata with states and transitions. It has each arc can have input, output, and a weight. And one of its main characters that help us is that we can compose different WFSTs one into the other, and thus combine the three models that I've spoken on, the lexicon, the language model, and the acoustic model, in a very compact and efficient way, and the recognition algorithm can run on it. And this is a small example. On the lower line, you see the acoustic model of the phoneme D. It has three states with transition and emission probabilities. The other line is the lexicon, and here we have the word data, its phonetic transcription. And into the phoneme D, we can actually enter the acoustic model, replace the arc of the D with the acoustic model, or at least point to the acoustic model. And the upper line is the language model. Here it's a bigram, and we can enter the lexicon word of data inside the language model. So this is just a small description of how this huge complex being created. Okay, so now we have a very nice ASR system. The performance of the ASR system today, as I've told you before, are similar to what human can do. Why do we still need to improve them? Well, the motivation is because of the language model nature of words. Most of the time, we are just saying frequent words that has very small meaning, like I, are, no, for, and words like that. For those words, we have a very good language model. And why is it so? We see them a lot in the training data. So the probability model for them is very accurate. But unfortunately, these words are not that interesting for our customers. They are much more interested in the company names, for instance. Now, the big name company like IBM, eBay, well, I guess we've seen them in our texts because they are familiar companies. So we do have a language model rather good for them. Not as good as the frequent words, but quite good. But what do we do with the small companies, which are actually the name of our customers and of our customers? If we have 1,000 customers, we can have 1 million names, company names. And those company names, most of them are not included in our lexicon even. And even if they do, the probability that they receive in the language model is the default, because we have never seen them in our training text. So what we want is to improve the recognition on these words. Here is a small example of motivation that Gong itself had. One of Gong competitors is the company Exec Vision, and it was recognized as Exact Vision, which sounds similar. And Exec Vision did not appear in our language model training set. Once we ended the classes model, this word is recognized now correctly. And you can think that the Gong supplies features like an alert to the manager is sent once the competitors' names appear in a specific conversation. So now we can do such tasks much better than we did before. Okay, so I'm back to the ASR model. Suppose the input sentence is, hi, this is Avinoam from Bilby Bag. And the recognition is, hi, this is Avi and Noam from Bill. Avi and Noam sound similar to Avinoam and are much more frequent names. so their model is better. And Bilby bag, we don't have in our lexicon. So the system recognizes a similar word like bill. Okay, this we want to improve. And how do we do it? We have one more resource of information that we can use. And this is what we add to our system. This is the metadata. Inserting the metadata in a clever way can help us recognize the words correctly. What kind of words can we get in the metadata? Usually our customers, as salespeople, when they set a sales appointment, they write the participants of the people in the meeting. They write the companies that participate in the call. They can keep a separate list of the competitors of the company and other special terms that are of interest for them, names of products, etc. And once we get this information, which can be specific for each call, we can use this information to improve the recognition. Well, one idea is to say, okay, let's increase the unigram of all these words. Okay? We know that there is a higher probability that they will appear. We know nothing about them. We can increase the unigram. This is not a good idea, since the context is very important, and higher n-gram will get the higher probability statistics, and the unigram will not pop up, or if they will pop out, they will pop out everywhere, and then we'll have many false alarms. So we need to insert them in a better way. And let's look at the example of the first name. What we want to do is to train a general language model for the class first name. How do we do it? We take our big training set and we look at all the first name that appears in this text. How do we find them? Well, we can download from the internet a list of common first names, and each place that we find a first name, we replace it by the first name class. Okay? And now we retrain our system. And now we get a language model for the first name class. And this is a part of the 4-gram statistics of the first name model that we've trained. You see that the words that have high probability to appear next to first name model match the first name context behavior. Okay, so how do we continue? What do we do now? We can take the list of frequent names, okay, of the 5,000th name that we found before, and give all of them the statistics of the first name. But this is not that good, such a good idea, because one thing is that it will increase the confusion between similar names, like Avi and Avinoam. And actually, we have a prior knowledge of a specific name that will appear in this conversation. It is not that all the 5,000 names have a high probability to appear in this conversation. It's only the ones that we received with the metadata. And also, this doesn't solve the out-of-vocabulary problem of names that we haven't seen before and that do not exist in our lexicon. So what we do is that insert only first name that are relevant to this specific call. So what is the flow now of the recognition? Do you hear me? The first stage is to look at the metadata, okay? And in this example, we receive from the customer the name of the participant in the meeting and the companies. We have Avinoam, Tamir, John, and Eyal, and the companies are Intel, Microsoft, Gong, and Bilby Bag. We look at each word and we look in our lexicon to find out if it appears or if it's not. If it's not, in this example, it's this company Bilby Bag, we run our G2P algorithms and receive the phonetic pronunciation. And now we go to the third stage and replace the first name class language model with the specific first name. And also in a similar way, we do it for the company name class.
So you generate the entire model?
No, in a minute. Excellent question. In a minute. Now we have the input. Hi, this is Avinoam from Bilbibeg, and using our new model, it is recognized correctly. Now, we can rebuild our big model again from the beginning, but this procedure is very heavy. It takes few minutes on a good computer. So it is not realistic to run on real time and rebuilding each time our whole graph. But we have another characteristic, very good characteristic of the WFST, that we can combine, again, as I've told you before, two WFSTs together. So we have our big WFST. This is the first line, okay, just part of the big graph that we have. And here I'm showing example of city name. It's like the first name. So between point 2 and 3, we have the arc of the city name, okay, with the language model that we've trained before, the class of city name. And now we know that in the input conversation, the cities that are going to appear or have high probability are Brno, Munich, and other cities in Czechoslovakia or Germany. And we build a very small FST. This is the second line. We build this FST that contain the specific city names. And then we replace the arc between nodes 2 and 3 with the small WFST. And this can be done very fast because it's just handling pointers inside the huge graph structure. So this is, in this method, we can do it in a fast way. Okay, here is some results. This is on 50 conversation tests that we have. And we tested it once with the base system on company names recall and of first name correct recall. And we received 58% on the first name and 52% on, 58% on the company and 52% on the first name. Part of those names did not appear in the lexicon. So with the basic system, we could not recognize them anyway. And then adding the classes model, we've improved the performance significantly. As you can see, the company names now get 84%, and the first name recall get 95%. So for a short summary, non-frequent words are the most relevant words and have high business value. They do not have good language model presentation. Using metadata, we can improve the performance. And a good way that we found that we can do it is using the context-aware classes in the language model. Thank you.